First law of thermodynamics. The first law of thermodynamics states that energy cannot be created or destroyed. The total energy of the universe is not changed by any chemical or physical change. However, the energy can be converted from one form into another and transferred from the system to the surroundings or from the surroundings to the system. Some of these conversions and transfers occur spontaneously. That is, they can proceed without any outside intervention. For example, a gas will spontaneously expand to fill a container. However, the gas will not spontaneously concentrate itself into one part of the container. Processes are spontaneous in one direction, but not in the opposite direction. For example, iron will rust spontaneously, but rust will not spontaneously break down into iron and oxygen. On the other hand, some processes are spontaneous above a particular temperature and not spontaneous below that temperature. In those cases, the reverse reaction will be spontaneous below that temperature. The classic example is the melting of ice, which occurs spontaneously at temperatures above 0 degrees Celsius. On the other hand, the freezing of water is spontaneous below 0 degrees Celsius. Reversible processes are those where the change can be undone by exactly reversing the process. This means that, under exactly the same conditions, the process can proceed in either direction. One example would be the swinging of an ideal pendulum, one with no friction or air resistance, where the potential and kinetic energy are changing, but the total energy remains the same. An ideal pendulum would keep swinging forever. No work can be done by a reversible process, and no energy is lost in the process. An irreversible process, on the other hand, cannot be undone by exactly reversing the process, because work has been done or energy has been lost. In order for a process to be spontaneous, it must be irreversible. Irreversible or spontaneous processes can be returned to their original condition, but work must be done for this to happen. Entropy is another energy function. The entropy is important in understanding spontaneous processes. The term is related to the heat transferred and the temperature at which it is delivered, as it was defined by Clausius. Entropy can be thought of as a measure of the randomness of a system. As the randomness increases, the entropy increases. The randomness is related to the various ways molecules can move. This molecular understanding of entropy was put forward by Ludwig Boltzmann. The molecular description is one that is much easier to understand and to apply to specific situations, as we will see a little later. Entropy is a state function, like internal energy E and enthalpy H. So the change in entropy, delta S, equals the entropy of the final state minus the entropy of the initial state. We can calculate the entropy change for a process in the same way we calculate the enthalpy change, using the entropy changes for the standard formation reaction of each substance. However, if we knew the absolute entropy, we will see later that we do, We could also calculate the entropy change from the absolute entropies, S rather than delta S. This is what we usually do. It is the absolute entropies that are listed in Appendix C in the book. Let's return to Boltzmann's molecular description of entropy. Temperature is a measure of the average kinetic energy of a set of molecules. There are several types of motion that molecules can exhibit. In addition to translation, that is, movement through space, other forms of kinetic energy are molecular vibrations, where the atoms within the molecule are moving with respect to each other, and rotations, where the entire molecule is spinning around some axis or part of the molecule is spinning, such as around a single bond. The larger the molecule, the more of these types of motions there are, and the more important they become in the total kinetic energy of the molecules. Boltzmann imagined a situation where he could glimpse the motions of a set of molecules at a specific instant in time, sort of like taking a picture of the molecules. He called this snapshot a microstate of the system. Each thermodynamic state of each system has a certain number of microstates associated with it. He gave this number of microstates the symbol capital Omega, a Greek letter. The entropy of a system is then S equals K times the natural log of omega, where K is called the Boltzmann constant and has the value 1.38 times 10 to the minus 23rd joules per Kelvin. Then delta S equals K times the natural log of the final number of microstates minus K times the natural log of the initial number of microstates. This rearranges into delta S equals K times the natural log of omega final over omega initial. We see that the more microstates a system has, the greater its entropy. So a system that changes will have its entropy increase if the number of microstates increases and decrease if the number of microstates decreases. The number of microstates increases as the possible motions of the molecules increase and as their ability to move freely increases. This means that entropy increases as the temperature increases, as the volume available for the molecules to move in increases, and as the number of independently moving molecules increases. Entropy increases as the freedom of motion of the molecules increases. This has an important relation to the particular physical states of the substances in a system. Solids have molecules that are locked in a regular array of positions, and so their freedom of movement is small. Therefore, the entropy of any solid state is small. In liquids, the molecules are free to move, but are still held close together by the intermolecular forces. So the entropy of a liquid is greater than the entropy of a solid, though still relatively small. A gas takes up much more volume and has individual molecules that are free to move throughout the whole volume. So it has the greatest entropy by a wide margin. For a solution, particularly of a solid in a liquid, the entropy is greater than that of a liquid, but still much less than that of a gas. Entropy will generally increase as we go from solids to liquids to solutions to gases, as the number of gas molecules increases, or as the number of moles of substances increases.